matrices and how to represent multidimensional data using matrices. As a reminder, a matrix is a rectangular array of numbers called elements, and we basically have an interesting concept of matrices, and that is the dimension. The dimension is the number of rows. In this case, let's say we have 1, 2, 3, by the number of columns. In this case, we have 1, 2, and 3. So we say that the dimension, the matrix A here has dimension 3 by 3. That is 3 rows by 3 columns. And the same way, we can say that a generic m by n matrix has m rows. So we have row number 1 up here up to row number m here by n columns, and that is 1 column up to n here. So we can basically represent the number of columns and rows by these matrix as opposed to just having rows of values. An important concept or an important kind of matrix is the row or column vectors. Those are matrices that have only 1 column or 1 row. So for example, this matrix B here, which is an m by 1 matrix, is said to be a vector because it only has 1 column. The same thing in this matrix here, 1 by n, and we say that this is a row vector. These will generally come up very often in regression analysis. Another interesting concept that we talked about is the transpose of a matrix, and that is interchanging the rows by the columns. In this case, we have the first row with values 2, 5, 7. That becomes the first column on the transposed matrix. The second row, 4, 8, 9, becomes the second column. So it's obvious that a matrix 2 by 3 will have a transpose that has dimension 3 by 2. We can also transpose vectors, and if we have a column vector, it will become a row vector when we transpose it. We talked also about the concept of two matrices being conformable for addition. So two matrices are said to be conformable for addition if basically they can be added. This concept doesn't translate into generic numbers because we can always add two numbers together. So 3 can always be added to 4.1. But when we translate that into matrix notation, not all matrices can be added. They have to be conformable first for addition. And two matrices are said to be conformable for addition if they have exactly the same dimensions. So in other words, a matrix m by n can be added only to a matrix that is also the same dimension, m by n. So for example, matrix A, 3 by 2, can be added to a matrix B, which is also 3 by 2. But the matrix A, 3 by 2, cannot be added to a matrix C, which is 3 by 4, because those two matrices are not conformable for addition. Okay, the same concept comes into play with multiplication. Matrices have to be conformable for multiplications, and the way to check that is the matrix on the left. We need to have the same columns here as the rows in the second column to be multiplied to. So these two numbers, n1 and n2, must always match. If they don't, then the matrices are not conformable. So for example, this matrix here, A, which is a 2 by 3 matrix, is conformable for multiplication to the matrix 3 by 2 because the columns on the first matrix is equal to the rows on the second matrix. And more importantly, the resulting matrix, and let's call it C, is going to have the dimension on the outer numbers 2 and 2. So this will be a 2 by 2 matrix. So these two matrices here are conformable. That's first. The result is going to be a 3 by 2. This matrix here, 2 and 4, don't match. So therefore, these two matrices are not conformable and the result cannot be calculated. Here we have result to be a 3 by 7, and the final one is going to be a 1 by 12. Okay. We also gave a few examples. We're not going to do matrix multiplication by hand, but one simple way to look at how it works when you multiply these two matrices together is that again, in this case we have matrix A, which is a 2 by 2, and matrix B, which is also 2 by 2. They are conformable, so the result C will also be a 2 by 2 matrix. Okay, so let's see what the results here are. We're going to multiply 2 times 3 and then add it to 1 times 7. So the result is going to be 13. So the value of here is going to be 13. Now the same thing happens with the rest of the calculations, and like I said, we're going to rely on computers to do these, but that is the reason why we must have the rows match with the columns, because that's the way it is calculated. Note also that A times B is not equal to B times A. Right? So an important concept that we will see often is that a matrix X, whatever its dimension, it doesn't matter what it is, when multiplied times its transpose, it's always going to be conformable. And another important concept is that it will always be what we call a square matrix. It will have the same number of rows as in columns. Let me give you an example. If I have X, which is a 2 by 3, and I multiply it by its transpose, and that transpose is a 3 by 2, that will always be conformable, and the result C is going to be a 2 by 2 matrix. And again, what we call a square matrix, because the rows will be the same as the columns. The identity matrix is a square matrix that has ones on the diagonals. So this is a 3 by 3 identity matrix here, and this is a 2 by 2. It is an important matrix because if you multiply something by the identity, you will always get it back without change. We came up with a concept that was extremely important, and that is the concept of linear dependence or independence. A matrix A is said to be linearly dependent if one of the columns or one of the rows is a multiple or a linear combination of another column. So let me illustrate it better. The first column on this matrix A is the numbers 1, 2, 3. Second columns 4, 4, and 1. It seems that column number 2 is not related at all to column number 1. But when you look at column number 3, it is actually a multiple of column number 1. That is, column number 3 is calculated by multiplying column number 1 times 3. So if I multiply 3 times 1, I get 3. 3 times 2, 6. 3 times 3, 9. So this matrix is linearly dependent because there is what we call a singularity. That is, a column is a linear combination of another column. We have to be in the lookout for those types of matrices. For example, in regression, when we have two columns, or in other words, two variables that are two related or even linear combinations of another matrix, then that creates problems, and we will see why. Another example, we have the same column number 1 and column number 2. Column number 3 doesn't seem to be exactly related to column number 1, but it is related to the two columns together. And in this case is 2 times column 1 plus column 2. In this case, this is also a linearly dependent matrix because column number 3 is calculated from a linear combination of the two columns, and the first two columns. So this matrix also has a singularity. Why are singularities important? And the main reason is because of something called the determinant. The determinant of a matrix is just basically multiplying the diagonals and subtracting the multiplication of the off diagonals. So for instance, if we have a matrix, let's say 2, 3, and then 1, 2, the determinant is going to be 2 times 2 minus 1 times 3, or 3 times 1. So in this case, the determinant of that matrix is going to be 4 minus 3, which is equal to 1. Okay, the determinant in this case is 1. The determinant is sort of a value that tells you the linear dependence of the matrix. And one thing that we will always note is that when the columns are linearly dependent, then the determinant is going to be 0. Okay, so the determinant is generally calculated when we want to get the inverse of a matrix. The inverse of a square matrix is going to be calculated by dividing every one of these elements, and we make some shuffling around of the elements and changing the signs, but we always divide all of them by the determinant. What that means is if the determinant is 0, we can't get the inverse of a matrix, and that is an important concept that we will come back later on. But for now, what we say is if there is a singularity on a matrix, we cannot calculate the inverse because the determinant is going to be 0. So let's switch to some code and basically explain the concept. Alright, so we're going to go ahead and practice a little bit with matrices and how to create them. So we're going to get started. Let's call these Introduction to Matrices in R. We're going to take a look at how to create first the matrix, some matrices, and we are going to create matrices with the function or the constructor, which is matrix. So this is what we call the constructor of matrices in R. So for example, for me to create this particular matrix, which has rows 7, 4, minus 3, 6, 4, 9, 1, 1, 6, I would create it this way. So I would just say matrix A is equal to, and then I would use the matrix constructor, and then I would have to put all of the values, ideally starting by columns. So we would look at the first column, input that, second column, and third column. So I can say, in order for me to put all of that, I need to concatenate the values inside. So I need to say 7, 6, 1, 4, 4, 1, minus 3, 9, 6. So all of those values are concatenated in there. The next thing is that I would have to let the matrix constructor know how many rows I have, and that is using the n row parameter, and that is number of rows. I can say this is equal to 3, and that would be enough for the matrix constructor to create the matrix. Optionally, I can say the number of columns as well, but if you just leave number of rows, the constructor will figure out that if you have 3 rows, it must have 3 columns for the matrix to fit. So let me just run this part, and right now we have a matrix A, and that matrix A has the values 7, 6, 1, 4, 4, 1, minus 3, 9, and 6. So again, this is what we call a square matrix. A is a square matrix because it has the same rows as in columns. Alright, so an important concept that we talked about was the dimension of a matrix, and we can actually get the dimension of a given matrix by using the dim function. So you can say dim of a given matrix, and then you can get the dimension of the function of the matrix back. So let me give you an example. Dimension of matrix A, and if I run this line, it will tell me that this is a 3, 3, which means it's a 3 rows by 3 columns matrix. Okay, so another concept that we looked at was the transpose of a matrix. So let me just put it here, transpose of a matrix, and we will use the T function to obtain the transform of a matrix. So for example, if I say transpose of A, remember that what the transpose does is that the first row will become the first column. So if I say transpose of A, I will just get back 7, 4, minus 3, 6, 4, 9, 1, 1, 6, and that would be the transpose of a matrix. Alright, so let's take a look at matrix addition. In order for us to get to matrices to conform for addition, they should be the same, exact same dimensions. So for instance, if I have matrix A, I can only add it to a matrix that has exactly the same dimensions. So let's create another matrix, let's say matrix B, and let me just take this matrix right here, and let's put it in R. So let's call it matrix B. So B would be 1, 2, 3, 4, 4, 1, 3, 6, 9. Remember, this is an example from the linear dependence slide. So this matrix is what we call linearly dependent, or it has a singularity, but it doesn't matter for adding. So we can also always add this matrix to anything else as long as it is conformable. So let's put it together. So we'll put the matrix function in there, the constructor, and then we'll concatenate the values 1, 2, 3, 4, 4, 1, 3, 6, and 9, and those are the values. I just need to do either number of row or number of column, and that would do the trick. So let's just do this, and then let's just get that matrix B. So I have it there. So in order for me to add A plus B, that is enough to do the matrix addition. And you can see that it is element by element added. Okay, so that is matrix addition. Okay. Before we do matrix multiplication, let's talk a little bit about a specific kind of matrices, and that is vectors. So vectors are either row vectors, which are basically have one row and multiple columns, or there are also column vectors, and those are matrices that have multiple rows and one column. So let me show you how to create. Again, let's create a vector C, and that vector, let's say it is a column vector, and let's do it. Let's do this example here. Let's suppose that this is matrix C. Okay, so we can also use the matrix notation, the matrix actually a constructor, and concatenate the values. That would be 4, 7, 3, and 2. And those are the elements, and then I will say that the number of columns is equal to 1. Okay, remember, you only need to set up one of the parameters, either number of columns or number of rows. If you put them together, it doesn't hurt, but you just really need one. So let's just put it here. So this C is a matrix with only one row, one column. And again, if you want to take a look at the dimension of that particular matrix, C, and we can see that this is a 4 by 1 matrix. Now, this matrix, we say that this matrix is not conformable for addition with a matrix that is a 3 by 3 because it doesn't have the same number of the same dimensions. So let me give you an example. For instance, I would say matrices A and C are not conformable for addition. And we can look at these. We say A plus C, and if we want to add those, you can see that you're going to get an error in R saying that they are non-conformable arrays, which is essentially they are not conformable for addition. Okay. Another concept of matrices is matrix multiplication. So let's do this particular example here, where we have matrix A, which is a 2 by 2, matrix B, which is a 2 by 2 as well. And let's take a look at matrix multiplication. And let's code this up. Let's say A, and let's use a matrix constructor. We have the values for matrix A is 2, 4, 1, 5. So we'll put it in there, 2, 4, 1, 5. We are gonna say that this has the number of rows equal to 2, so I don't need to set anything else up. That would be enough. So let me look at the matrix A, and it is a 2 by 2. Now let's take a look at matrix B, and let's construct it by using the matrix function, and I'll concatenate the values 3, 7, and 6, and 9. The number of rows is also 2. Okay, so we're on this part. So we have matrix A and matrix B. Both matrices are 2 by 2. So these two matrices are conformable for both addition and multiplication. But the way that you would look at multiplication is that you have to see that the columns of matrix A have to match your rows of matrix B. Multiplication in R is done multiplication of matrices is done with the percent asterisk percent function. In other words, if I want to multiply A times B, I can't really do these. This would not be something that would work for matrices. I would need to do that would be the percent asterisk percent, and in that way I can multiply these two matrices. So if I run that, I would get the values of 13, 21, 47, and 69, which is what we got here. That would be A times B. If I want to get B times A, then I can run that, and then I would get the values 30, 50, 33, and 52. So you will know that A times B is generally not B times A. Okay? All right. So let's go to another concept. And that concept is the concept of determinants. All right. So let me show you what the determinant of matrix, let's say A, which is the 2 by 2, is going to be 2 times 5 minus 1 times 4. There is a function in R that calculates this for you because it becomes more difficult to calculate if it is a matrix of greater dimensions. But one thing that you have to note is that the determinant is only calculated on square matrices. Okay, and we use the det function. So let me show you an example. Det of matrix A is a determinant of matrix A, that would be 6, and again it's calculated easily with a 2 by 2 matrix. It's 2 times 5, which is 10, minus 4, and that would be 6. If I want to get the determinant of B, I can do it with this det function, and that is minus 15. So you can see that the determinant doesn't necessarily have to be positive. But one thing to note is that when the matrix is linearly dependent, and let me give you the example one that we gave here. Matrix A, which has these columns, column 3 is a singularity, which means that it is constructed out of the columns of another matrix. So let's have it here. So we have the code for this here. So we called it B. So let's take a look at the determinant for a singular matrix. And that is actually this matrix here. Let's call it A. So that we have the exact same sample. So we have this matrix here, A. We said that this column number 3 is calculated by multiplying 3 times the first column, so we know there is a singularity. So if we want to get the determinant of that matrix, it's got to be 0. So the determinant of a matrix that is a singular matrix, or that it has a singularity, will always give us a 0. There's another example of a singular matrix. So let me just write this here. A has a singularity. Let's create matrix B. Matrix B here is also singular matrix. It is third column is 2 times column number 1 plus column number 2, so it does have a singularity as well. So let's construct it. So I'm gonna concatenate it: 1, 2, and 3, 4, 4, and 1, 6, 8, and 7, with the number of rows equal to 3, so that's matrix B. We said this is a singular matrix, so when we get the determinant of this matrix, it's also going to give us a 0. You will note that sometimes you will get a value like this, e to the minus 15, which is essentially a 0 up to precision. It's a different precision computed by the computer, but it's basically a 0. Right. So this is going to become important because what happens is that in order to get what we call the inverse of a matrix, so let's talk about the inverse of a matrix. The inverse of a matrix is calculated using the determinant. So for instance, if I have this matrix A here, and let's copy and paste it, I can calculate the inverse of this matrix using the solve function. So in order for me to get the inverse of these particular matrix, I would do solve A, and that would give us the inverse of matrix A. So if I do that, the inverse would be this value. The inverse of a matrix is sort of dividing, it's just sort of 1 divided by the matrix. It's sort of that, you can think of it that way. But what happens when the matrix is not invertible, which means that you can't invert the matrix, that happens when the determinant is equal to 0, because you can't divide something by 0. So in fact, if I do this matrix B here, this matrix has a singularity, so I can't really do solve B, because that matrix can't, there is some of these elements here that need to be divided by the determinant, which is equal to 0, which in this case will give us an error. So you will see that error, system is computational singular, meaning that the matrix is singular, or there is a singularity, and that is an important concept that we have to take into account when we do regression. Right, so that's pretty much it on the matrix practice.